So, hello all. Welcome to this session on modeling and simulation of dynamic systems. So, my name is Parth Joshi, and I have been conducting these online tutorial sessions for the last 2 weeks, and this is a third week. So, this will be our third session. So, I'll just quickly introduce myself. So, I am basically a PhD student in the Department of Mechanical Engineering at IIT Bombay, and I'm basically a recipient of the Prime Minister's Research Fellowship. And as a part of that, this fellowship, so I got an opportunity through NPTEL to conduct these online interaction sessions with all of you. So that's how basically I am here, and I have been basically working in the area of like basically modeling simulations for automotive systems like electric and hybrid electric vehicles. So that has been my core area of research in my masters as well as in PhD. So I did my masters also at IIT Bombay and with the specialization of design. So that's about myself. So I think most of us have joined. So I think we can get started with today's session. So Vishal, I think you were saying something, wanted to say something. No? Okay. Okay, then yeah, so then this is the third week's problem solving session. So before we get started, I wanted to ask whether everyone is clear with the content for this week, or if anyone has any difficulty with the content which was covered earlier, or anything like that. If not, then we can just get started. So I have some sample problems for you. So we can actually just get started with solving those problems. Uh, so the content for this week is basically it deals with uh, how to basically now it starts with the building blocks for the systems from various domains. So electrical, mechanical, hydraulics, pneumatics, and thermal systems. So to develop the models for any system, so which has energy exchange between multiple domains. So we need to first establish what are the different building blocks in each domain for modeling the subsystems or components which are present in a system. So if they are like mechanical components, so then there will be certain building blocks. So the building blocks were for a mechanical systems were basically springs, masses, and dampers. So whatever mechanical systems or mechanical components, so we can model them as a combination of mass, spring, and dampers, depending on what is the problem that we are looking at. So it's not necessary that we need to explicitly have springs, masses, and dampers present in the system. We can model the behavior of the system in, and we can construct it in and represent it in a way that is which is essentially a combination of mass, spring, and damper. So we had seen some examples earlier, like we had seen how we model a car. So the car body, it is actually made up of multiple, like the car itself is made up of multiple things, but we just consider the whole mass as a one single block, so that we basically lump the entire mass of the car into one block, and we represent it as one single block of mass m, and we consider the stiffness and the damping characteristics of the suspension. We model it as a single, let us say single spring and damper, and then we also consider the tires. So then we lump together the mass of the tires. So in reality, the mass is always distributed, but we just lump it into a single mass. So we call it, then we represent it as a, a single mass. So then, so so let me just open up one of the slides so that uh, it will help you understand what I'm saying. So it was, so I'm sharing my screen. So is it visible to you? I'm sharing one of the slides for the, yeah, yeah. So basically this shows like the model on the right hand side. So it shows the how we model the car. So we have the car, it is lumped together as a single mass, and then we consider the suspension and the tires separately. So uh, and the stiffness of the tires, we can also consider damping. So although it is not shown over here, so we can also consider the damping present in the tires, because the tire material is also it's made up of rubber, which is a viscoelastic material. So there is some hysteresis, basically when it goes through cyclic loading and unloading, there is some loss of energy, so then that can also be represented as a damping. So so this is how we can use this approach to model more complex systems. So yeah, this was for mainly for mechanical systems, but similarly we have like other building blocks in other domains, like for example electrical systems. We have basically the building blocks as resistors, capacitors, and inductors. So there can it's more I think more intuitive and easy to visualize that the components are explicitly either resistors, capacitors, or inductors, or and there may be other electrical and electronic components which may have some similar properties. So we could model the electrical circuits in terms of those properties. And then we have again hydraulic and pneumatic systems, where uh, they are basically just basically fluid power is being used over there. So in hydraulics and pneumatics, the essential difference is in the working fluid. So in hydraulics, it's generally oils are used, or basically liquids. So those are basically incompressible fluids, whereas in pneumatic systems, the fluid is generally air, or basically a gas, which is a compressible fluid. So so again, the behavior of these hydraulic and pneumatic systems can be uh, represented in terms of like capacitors, resistors, and inductors. So inductors or in inertance, what they call here in case of hydraulic and pneumatic systems. So these are analogous to the uh, corresponding electrical components. So their equations are of the similar form. So that's why you can say they are called as either resistor or inductors and capacitance. So those are the building blocks for the pneumatic and hydraulic systems. And similarly, we have the thermal resistance for thermal systems and thermal capacitance, etc. So uh, these were the key points that were related to the content for this week. So now I have some sample problems for you, so we can start with solving those problems. So before that, are there any questions or comments? Okay, so fine. So then we can start with. So now let us get started with the problems. So the first question is, the damper constant in the mechanical system is analogous to what in the electrical system, as per the typically what is considered 1 by r. Okay, so why is it 1 by r? Any idea about why is it 1 by r? So the equation is basically force is equal to c into x dot, and the equation for a resistor is I into r. So which of these terms are like analogous? Okay, so basically, yeah, right. So basically the velocity is analogous to x dot, and the force and current are, so we need to basically rearrange the equation slightly. So basically we write v by r is I, and so that's why like, so f, so cx dot is basically force. So then that's why we can say that c is then analogous to 1 by r, right? Because the proportional constant here is in this equation is 1 by r, whereas here it is c. So the proportional constants are basically analogous. So the damping constants, so that's why it's analogous to 1 by r. So now here in this next problem, we have a mechanical system over here. So there are lots of mass, spring, and damper things that are shown over here. Now we have to find out, basically derive the mathematical model of the system. So mathematical model in the sense, basically some differential equation that represents the behavior of the system. So there will be basically uh, two unknown positions x1 and x2, and there is a force Fe applied over here, and this mass is sliding over some floor over here, and there is a some kind of friction between this mass and the wall, so that can be represented by this damping constant b1. So let us assume that this is viscous damping. So we'll assume that this is also like viscous damping. So then the form of the equation will be something like v1 into the corresponding relative velocity. So how do we start solving this problem? So what is the first thing that we need to do? So how do we start uh, approaching this problem? Right. So we have to draw the free body diagram of each component separately. So here this block of mass m1, uh, so that has a displacement of let us say x1, and the point which is connecting between the joint between the springs k2 and k3, that has a displacement of x2. So now we have to draw the free body diagram and show the forces acting on each component separately. So let us start drawing the free body diagrams of each component. So the let us first draw the free body diagram of the block of mass m1. So first there is a force Fe acting on the mass m1, and then there will be, what will be the other forces? Yeah, so there will be a force k1 x1. Now how do we decide the direction? So basically this, let us say the mass m1 is moving towards the right hand side, and we assume that the spring is stretched because of the displacement. So the displacement here, let us say it's in this direction. And now for the spring k2, now how do we decide the direction for that? So let's draw the diagram, free body diagram for the spring first, like k1. So its one end is fixed. So so it will, so the force acting on both the ends will be k1 x1 itself. Now in case of the spring k2, both of its ends are being displayed, the displacement of both the ends are different. Now one more thing is that we will assume that this displacement x1 and x2 are basically with respect to its equilibrium position. So then whatever x1 or x2 is the net deflection. So then now the force acting on the spring K2 will be proportional to the difference in the displacements of the two ends. So basically it will be, so let us assume that x2 is, for the, like for this, let us say the time instant that we are looking at, let us say we assume that x2 is greater than x1. So then what will happen? Then the spring K2 will get stretched. So then the spring force on the K2 spring, we can write it as K2 into x2 minus x1. So we can show it as a, that the spring is in tension. So we could also look at it either way, that that the spring is in compression, but then we need to change the direction of the forces accordingly and just carefully put the forces in the free body diagram and write the equations properly. So whatever sign convention or whatever that we follow, so we should make sure that we are consistent. So we show the spring force K2 into x2 minus x1. And then let us say we also assume that x1 dot, like the velocity is also in the this direction. So there will be one more force because of the uh, friction between this mass and the floor over there. So then there will be the damping force B1 into x1 dot, because the relative velocity of the mass m1 with respect to the floor is x1 dot, right? And then we can also show the uh, free body diagram for the spring K3. Now because this is the spring, the this point, let us say, let us call it as P, this the joint at that is moving towards the wall. So then the spring K3 is being compressed. So we will show the force as compressive. So then the expression for the spring force, it will be basically K3 into x2. And similarly we also need to show the free body diagram for the damper. So now since the velocity x2 dot is towards the right hand side direction, then the damping force will be opposite to it. So right? So this is the free body diagram for the damper. So we have now drawn the free body diagram for the all the components. Now at the point P, there is actually no mass present at this point. So then what will be the relation between the forces acting at that point? So what will be the relation between the forces acting, like basically the relation between the spring force and damper force over there, like at that at which are acting at that point? Anyone? Yeah, so the net force acting at that point will be zero because there is no mass. So this net force is basically, let us say, the mass into acceleration of that point. So the point P will have some, let us say, some acceleration because x2 dot x2 double dot need not be zero. But since there is no mass, the net force must add up to zero. So that's why, so the forces need to be in certain relation. So we'll write down that equation also. So now see, so we are done with the basically drawing the free body diagram. So now our next step is to write down the equations by looking at the free body diagram of each component. So let us write down the equations of motion for the mass m1. So we have the, so we'll first write down the sum of the net forces. So when we write the equations of motion, so we basically write down the Newton's second law for that component. So basically summation of the net forces is the mass into acceleration. So the net sum of the net forces is basically sum of all these forces shown on the free body diagram. So this will be the equation of motion for the mass m1, and similarly we can write down the equation of motion for the point P now. That so basically for that, so we can show, like, the point P here. So at the point P, so we have the spring force. So let us say if there were some point mass present at P, so then the forces acting on it would be, So the spring force due to K2, and then there will be a force because of the damper and the spring. So it should be K3 into X2 dot. So these will be the forces acting at the point P now. So if there were some arbitrary point mass, so we can write it as let us say, so minus K2 into X2. So minus because it is acting on the left hand side, and we are assuming that the right hand side is forces acting on the right towards the right hand side are positive. So but we are given here so that the mass of P is actually 0. So then so this will be basically the net force acting at that point P, so which is 0. So therefore the spring and damper forces will be constrained to be as per this equation now. So these will be the two equations of motion here. So since we have two variables x1 and x2, so these are two degrees of freedom. So therefore we need two differential equations to be able to solve this the or to be able to basically exactly identify and completely describe the system behavior in terms of x1 and x2. So this was how we get the equations of motion. So we can rearrange them in suitable forms. So let us say the first equation, if we move the terms on the left, some of the terms like the spring and damper forces on the right hand side, then we can get the equation as the sum of the inertial force, spring force, and damper force is equal to the external force applied. And the next equation is basically the constraint on the other forces. So this was about the equations, how we derive them for this kind of mechanical system. So any questions on this? Any questions or comments? Shall we proceed? Okay. So here we have this problem which is related to thermal systems. So it says that there is a industrial furnace wall made of fire clay brick, and it is zero point 0.2 meters in thickness, and Measurements during steady state operation showed that the temperatures on the inside and outer inner and outer surface of the furnace wall, they are 1500 and 1100 Kelvin, and we have been given the length and the height of the wall and the thermal conductivity for the fire clay brick. So what we have to find out is how much is the heat conducted through the furnace wall. So how do we solve this problem? So anyone has any idea how do we solve these kind of problems? Okay. So no one has an idea. So has everyone how many of you who are attending this session? So how many of you are from a mechanical engineering background? So can you just raise your hand? Could you just raise your hand? So none of you are from mechanical engineering. Okay, one. And how many others? About the others, are you from mechanical engineering background? Electrical. About and the others are others are also from non mechanical backgrounds. Aerospace. Okay, fine. So you can count it as somewhat like mechanical itself. But yeah, and in how many of your like undergraduate students, like undergraduate BTech, BE, BTech students? Okay, so okay, fine. And others, like, are you? What about the others? Are you graduate or postgraduate or like? So Bishal, so you're a postgraduate student, okay? And Rahul, Arvind, Srivalli, and Venkata. So all what about you? So you are MSc, okay, fine. MSc in physics, okay, okay. And then Rahul Kumar, Arvind, what about you? So are you from mechanical engineering backgrounds? Now the reason why I am asking this question is that some of these concepts which are covered, like let us say from the especially like the modeling of mechanical and thermal systems and the pneumatic and hydraulic systems, so it may be kind of easier to relate for mechanical. Okay, so you are tech in machine design, okay, fine. Venkata. Okay, fine. So yeah, thanks. So basically just I'm trying to get the idea of what is the typical background uh, from which all of you are coming. So then I can either assume or not assume what you might have learned. So generally the uh, thermal related concepts, so then generally are covered in the second and third year of mechanical engineering undergraduate degrees. But the electrical people from the electrical background may not be so familiar with that. So then I could just just briefly explain the basic concept on that. Fine. So I think some of you are from non-mechanical engineering background, so maybe just we can quickly go over the okay, Balbhim. So you are, yeah, from MTech Control Systems. Okay, fine. Thanks. Sure. So then, so this problem is dealing with the concept of conduction, heat conduction. So we have the Fourier's law of conduction. So which says that the net heat flux, let us say Q double dash, which is passing through like the surface, is basically proportional to the temperature gradient across the surface. So basically, how we write it as the so the heat flux is proportional to the temperature gradient. So let us say if we are dealing with a single first like one dimensional heat conduction. So then the constant of proportionality is known as the so here K is basically the thermal conductivity. So I think someone said that they were from physics background, so they might know he or she like I think Venkat. I think he said that he is from physics background, so he might be knowing this already. But others, I am not sure whether you have covered this in your uh, whatever like undergraduate or postgraduate curriculum. So then K is the thermal conductivity, and the tip generally the unit is watt per meter Kelvin. Now, if we are considering a single wall, now if the thickness of the wall, let us say the thickness T, and the other dimensions of, let us say, the wall are basically the length and the height. So if the thickness is much smaller than the length and height of the wall, then the we can essentially consider that the heat conduction is during steady state, of course. Heat conduction is nearly one dimensional, so it is along this. So there will be, so if the the temperature across the entire surface of the wall, if it is nearly constant, so there is no variation. Let us say if this is if this is our, let us say, x direction, and then this is our y and z direction. So then so the temperature variation along the y and z direction is negligible. So the wall surfaces are, you can say, isothermal. Then there will be no heat flux in the along the surface, so there will be just heat conduction along the x direction. Then uh, so then we can apply this Fourier's law. So the heat flux, it can be, so if this, so it will be generally along this direction. So the heat flux, so either it could be in this direction or this direction depending on what is the temperature of the wall. So let us say if this wall is at temperature T1 and the other surface is at temperature T2, and if T1 is greater than T2, then heat will be conducted from the higher temperature surface to the lower temperature surface. So it's basically in the heat flux is opposite to the direction of the temperature gradient. So that's why we put a minus sign. So it's actually minus K del T by del X. So then that's why, so if T1 is greater than T2, then we say that the heat flux is in this direction, Q double dash. So here we have been given that T1 is 1500 and T2 is 1100. And we have been given that K is 1.7 watt per meter Kelvin. So now we can find out the heat flux, which is basically the heat energy passing through the wall per unit area. So which is basically minus K into del T by del X. Now here we assume that the material is uniform, and then that's why the temperature distribution is linear, because if the thermal conductivity K is constant across the entire wall, so if it is a uniform wall, so then K is nearly constant. So then the temperature distribution will be linear. So say if the temperatures T1 and T2 are always maintained at these values, then the heat flux will in the steady state it will be constant. And since if K is also a constant, so then therefore del T by del X will also be constant. So let us call this thickness as T. So then we can write del T by del X as T2 minus T1 upon thickness T. So which is basically linear. So we can assume that the temperature distribution is linear. So so the temperature, let us say if our origin is here, so then so at x is equal to thickness T, the temperature is T2. So this is how we can write the temperature gradient now. So now we can calculate the heat flux using this as, so it will be minus K into, and then we can substitute the values of the temperatures T1, T2 and the thickness T. Um, and now the heat energy that is uh, flowing through this wall So it will be basically the flux. So this will be the flux in terms of watt per meter square, and the net heat energy conducted, that will be basically the flux into the cross sectional area of the wall. So basically it will be this q double prime into length into height. So the length into height is also given to us. So it will be basically k into, so the q will be, so what is the answer that we get if we substitute these values? Can someone just try calculating this thing? Can all of you try to calculate what is the value that we get for the heat energy k q? Okay, so let me just check. Uh, so the temperature difference is 400 Kelvin. So into 1.7, and the length and height are given as 1.2 and 1. So it's basically, so 1.7 into 400 into 1.2, and the thickness is zero point 0.2 meters. Yes, it is 4080. So 4080 watt is the heat energy that is being conducted. So it's a simple problem, but why I actually explained it slowly with each step, so that we understand clearly what are the simplifying assumptions that we take. So although the problem may appear to be simple, but in reality, here we assume that the heat conduction is one dimensional, but in reality is never, it is one dimensional. So if the wall is big enough, then we can nearly assume it to be one dimensional, but in reality it will always be three dimensional. So there will be always heat flow along all the directions. So make sense? So let's move on to the next problem. So here let us say we have a composite wall, or basically a wall which is made up of multiple materials. Let us say A, B, C, D, some materials, and let us say heat is flowing from the high temperature surface, uh, which is at 400 degrees Celsius, and the heat is flowing out at the other low temperature surface, which is at 60 degrees Celsius. So there is, so the end temperature at the end is, let us say this, we call this temperature as T1, and this as, let us say, T2. So at the end, so then in between we have the material A. So if we look at this from this side, so heat is flowing in and flowing out from here. So this is the material A, and then in between we have this layer. So this has, let us say, thickness TA, and this thickness TB and TC both are equal. Now if we want to find out what is the thermal resistance, which is basically of this wall, so how do we go about solving this problem? So anyone has any idea how we can solve this kind of a problem? So think, you can think in terms of the electrical analogy of this. So let us say if we have a, different resistors in series and parallel. So how can we apply that kind of an analogy in this case? Yeah, so we can take series and not only series, but there are other if we look at these slabs like B and C, what can we say about them? They are in parallel, right? So the block A and then the resultant or combination of blocks B and C and block D, they are in series, right? Yeah. So then what we can say, like we can represent the thermal resistance. So we'll come to how we calculate the thermal resistance, but let us say like we just draw the diagram like an electrical circuit. And now the resistances of B and C, so they are in parallel now. So we can solve it using the similar resistance type of analogy. Now, similar to, let us say, if there is the potential difference across the two ends of the resistances, like the net resistance. So similarly, we have the two temperatures at the two ends. So they are analogous to potential difference or voltage in that sense. So and the heat flow will be analogous to current. So basically, Q will be analogous to current, and the temperature T is analogous to voltage. So basically we, in some sense, so because V is equal to I into R, so similarly Q into some resistance will be basically, in some sense, we will get an equation of this form. So where, since Q is analogous to current and temperature is analogous to voltage, So we'll come to how we actually write down the expression for thermal resistance. So we know that the from the Fourier's law of conduction that we just discussed. So this is the Fourier's law of conduction, and if our material is uniform and homogeneous, so then therefore K is constant and the cross sectional area is also constant. So then and at those, so therefore so this is also applicable to the steady in a steady state condition. So the heat flow, we can write it as into delta T upon the thickness of the wall. So in case of the slab A, let us say if we call this temperature as T3 and the temperature at this interface as T4. So then, for let us say for the material A, so let us write it as QA. So it will be KA into area, and the change in temperature across. Uh, since this is a minus sign in case of Fourier's law, so it will be basically minus T3 minus T1 upon TA. So this will be the heat flowing across the material A. So let me just write it down again on a new page. So this is the heat flowing through the slab A. Now similarly for B, we can write down as, so the temperature at the two ends are T4 and T3. So it will be basically T4 minus T3 on TB. And then the heat flow across the material C and D, we can write it as similarly as Kc into AC. So these are the expressions for the heat flow, or basically it's like the expression for the current passing through the resistor. So the heat flowing here will be QA, So in steady state, what can we say about the relation between all these values of QA, QB, QC, QD? What can we say about them? If we look at the circuit, then what can we say about them? If we want to say that the heat flow is analogous to the current, then how will we write the relation between the heat flow? So consider the Kirchhoff's current law. So if we look at each junction points, then what can we say about the values of the heat flow? Right. And other about what about the other relation? Sorry. Yeah. Right. Exactly. Right. So so the same heat flow is being distributed across the materials B and C, and so QA is equal to QD, right? So because they are in series, so the same current will flow through this them. So we have the expressions for the heat flow now. So if we want to derive the analogous expression for the thermal resistance now, so we can rearrange these equations in the form of basically, so it's basically in the form of Ka into some delta T by some thickness. So so V upon V upon I is the resistance. So in that, if we rearrange it in that form, so then delta T by Q is analogous to voltage by current, and which is equal to, so the resistance, thermal resistance is basically the proportional to the thickness and inversely proportional to the thermal conductivity and the cross sectional area. So we can derive the expressions for Ra, Rb, Rc and Rd using this expression over here, T by Ka. So Ra will be Ta by Ka into Aa. And similarly, we can write down the expressions for the other resistances, like Rb is Tb upon Kb Ab. So since we have already know the dimensions of the that block, so we can easily calculate the cross sectional area and the thickness of each slab, and so thereby we can also basically calculate the thermal resistance now. So what will be the equivalent thermal resistance? So it will be, so equivalent resistance of B and C is basically, so So it's basically 1 by R equivalent is. So we can write it in the similar way as we write it for, since they are in parallel. And then the total uh, thermal resistance between the ends of the wall will be basically RA plus R equivalent plus RD. So everyone was able to understand up to this point. So am I going too fast or too slow, or like if you can also just let me know if if I am going too slow or too fast or whatever. Anyone wants to say something? Am I going too slow or too fast or okay? Okay, fine. So since we have been given the dimensions of the the cross section, so we can calculate now the so I'm just redrawing the figure so that it's easier for us to calculate the values. So the thickness of A is basically 0.03 meters. So this is in centimeters. So the cross sectional areas of each of these layers we can calculate it based on the dimensions. and 150, 30, 65. Yeah. So these are the values of all the parameters. So can all of you just calculate the values of the resistances and then the total resistances? So maybe you can take the next 2 or 3 minutes to calculate. So has anyone calculated the value of RA, RB, RC, or RD? Okay. 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 08 0.083. Okay. Uh, how did you get 0.083 for RD? Actually, I am getting zero point 0.1. Anyone else is also getting the same answers? So this is 50, by the way, if it is not clear. So I am getting zero point 0.1 over here. Rest of the values I am getting them the same. So the thickness of D is 0.05 and KD is 50 and the area is 0.01. So it's basically 0.05. Yeah, fine. So we get these values of the resistance. So now we have to find the equivalent of these two. So they will be okay. 0.146. Okay. Right. 1.146. I am also getting the same thing. Right. So basically, then we need to add these three to get the final equivalent. So it will be basically zero point zero 0.02 plus zero point 0.1 plus 0.146 will be our total. So it will be about 0.266, right? So yeah, so that's how we calculate the thermal resistance. So any doubt? So let's move on to our next problem. Now since we have covered a mechanical system problem, so let's first, since we have not covered electrical systems, so let us look at a problem with respect which deals with electrical system. So here we have been given a RLC kind of circuit where we have inductors, capacitors, and so it's given that in these loops the current I1 and I2 is flowing. Then we have to basically derive the equations the governing differential equations for this circuit. So how do we solve this kind of a problem? So we apply basically the Kirchhoff's voltage law or Kirchhoff's current law, whatever that we find useful. So if we apply Kirchhoff's voltage law for each, so so for the first loop, let us say if we apply the Kirchhoff's voltage law, so we basically in this law we basically write down that the net um, net like voltage difference across the entire loop is zero. So if we label these points, let us say as A, B, C, and D. So if we start and travel along the loop in the direction of the current, then we note the potential drop across the loop. So let us say if we move from point B to A, there will be an increase in the potential difference. So that will be, let us say, EI. And as we go along the direction of the current, so there will be a voltage drop. So it will be I1 R1 across the resistor. Voltage drop across the resistance is I into R, and then the voltage drop across the inductor is L di by dt. But here we have, so this inductor is between common between the two loops. So what is the net current that is flowing through the inductor? Right. So I1 is flowing in this direction and I2 is flowing in this direction. So the net will be I1 minus I2. So it will be basically L into d by dt of I1 minus I2. And then this is how we complete the loop now. Now if we look at the second loop, then let us start from the point C. Then we can write as minus I2 R2. Now the voltage drop across the capacitor C. So it's basically the it's basically Q by C. So the charge stored in the capacitor will be integration of the current that has flown through the capacitor. So we can write it in this way. and then we write the voltage drop across the inductor. Now since we are traveling in the direction of current I2 now, so then we could write it as L into d by dt of I2 minus I1, so which is equal to 0. So this is for the second loop, and we have been given that the potential difference between EF is E0. So basically 1 by C integral I2 dt, which is the voltage drop across the capacitor. So that is given to be E0. So this is how we can use the Kirchhoff's voltage law to derive the equations of motion. We could also apply the Kirchhoff's current law, but for that we need to clearly indicate what are the different current currents that are flowing through each component. So, so let us say if across the inductor we say that the current flowing is, let us say, I1 minus I2, and here this is I2. So, and the current across the inductor is, let us say, I1 minus I2. And then we can use the each of the junction points to uh, write down the Kirchhoff's current law for this junction. Let us say the point C. So what we can write as the voltage across VA minus VC upon R1 is basically is I1, and VC minus VE upon R2 we can write it as I2. And we also know that VC minus VD, so we can rearrange these equations to basically, so this is how we can write down the expressions, and then we can solve this equation for the potential. So if we assume that the points D and F are grounded, so like VD is equal to VF is equal to 0. then we can simplify this equation slightly and then solve this equation for the um, voltage VE, and in terms of the currents. So VA is already known, so that is EI, and the voltage VE is also already known, so that is E0. So using this approach, we can also solve the equation, like the we write down the equations in this way using the Kirchhoff's current law. So any questions? So let's move on to our next problem. So in case of hydraulic capacitance, the energy storage in the liquid is in which form of the energy? So how do we answer that? Right. Yes. So it is in the form of potential energy. So the height of the liquid column, so that will lead to uh, like basically the pressure, um, and that energy is stored in the form of potential energy, or basically the pressure head at the base of, let us say there is a container and the fluid is contained in it. So the pressure at the base is because of the hydrostatic pressure at the base, so that is the pressure head at the bottom, so that is stored in the container in the form of potential energy. Yeah, so this is, we have this another simple problem related to thermal systems. So we have a wire which has a certain diameter and length, and it is submerged in water at atmospheric pressure, and an electric current is passed through the wire, and it is increased until the water boils at 100 degrees Celsius. So if the convective heat transfer coefficient is given, uh, then we have to find out how much electric power that we need to provide so that the wire is maintained at the surface temperature of the wire is maintained at 120 degrees Celsius. So let us just first draw the diagram for this. So this wire is submerged in water, and let us say we are applying some voltage across the terminals of the wire, and since it has some resistance and some current I is flowing, so the heat generated across the resistance, that is the I square R, so that is the power that is dissipated across the resistor because of the current flowing. So that heat is basically used to heat the water. So this wire has a certain diameter and length, so we can draw it as a cylinder, So let us say the diameter is, or the radius is r, and the length is, let us say, l. Now what we are given is that the convective heat transfer coefficient is given, and we have been given that the surface of the wire is maintained at 120 degrees Celsius. So now the surrounding water is boiling at 100 degrees Celsius, whereas this surface is at 120 degrees Celsius. So now for this system to be at steady state, the heat that is being generated inside the wire because of the current flowing, so that power, it should be uh, same as the power that is being given to the water in the form of convection. So so basically this power I square r, it should be same as the heat transfer because of the convection. So let us say the convective heat transfer coefficient is given as h, and the, let us say, the surface area of the cylinder across which the convection heat transfer is happening. So the heat transfer due to the convection, so it can be written as HA into Ts minus T infinity. So T infinity is basically the surrounding temperature, which is 100 degrees Celsius, so for the water, and the surface temperature is given to be 120 degrees Celsius. Now what is the surface area here? What is the surface area across which the heat transfer is happening? Is it only pi r square? So what will be the curved, like the surface area of the cylinder? Yes. So not pi r square L. So that will be basically the volume. So the area will be the area of the, yeah. So it will be basically 2 pi r into length plus the surface area of the two ends. So let us say 2 into pi r square. So now if our actually the diameter is very small, so we could actually just neglect this part 2 pi r square, if at all, because it's a very small wire, and it is, so the length is much greater than its diameter. So then we could actually just neglect and just say 2 pi r l. So the heat is being, like, if we look at it from the top, so the wire is, the heat is being transferred in all directions radially through convection, and the heat that is being generated because of the resistance of the wire, so that is being transferred to the water. So this is how we can write the equation for heat transfer over here. So this is how we can solve this problem. So I will not go into the calculation right now, so you can try it on your own. So since we are short of time, uh, so anyone has any doubt? So let's just quickly discuss our next problem. So here we have been given a mechanical system. So this is somewhat similar to what we had done earlier. Like the difference is only in the slight differences in the arrangement. Uh, here we have two masses now, and they have been connected together through a spring and a pulley, and it's given that the pulley is ideal. So here also we have to go through the same steps of drawing a free body diagram of each component and then write down the equations of motion. So let me just quickly discuss how we can draw the free body diagrams for this kind of system. So it's given that the x1 is in the left hand side direction. So and another external force is also applied to the mass m1. So let's draw the free body diagram of the mass capital M1. So there is a force Fa. So we will assume that x1 dot is also in this direction, and similarly here in this case x2 dot is also in this direction. So there will be a viscous damping force because of this uh, friction between this mass and the floor, and then the spring force will be k1 into x1. So because the spring is getting stretched since it is moving towards the left hand side. Now let us draw the free body diagram for the mass M2. So because it is moving down, so the spring is getting stretched. So the force in the spring will be K2 X2. So here we assume that X1 and X2 are with respect to their respective equilibrium positions. Only then we can write that the spring force is that way. So this will be the force because of the damper, and in addition to that there will be tension in this string over here. And let us draw the diagram for the pulley. So there will be tension in the pulley across the both the ends, and now this, because this string should remain always stretched, this tension will be equal to the spring force k1 x1 itself. And since it is given that the pulley is ideal, that is why, so we could actually write it as tensions T1 and T2. And if the pulley was not ideal, the tensions T1 and T2 would have been different. If like so in the sense, when I say it is ideal, so it means basically massless and frictionless. So if it is uh, both massless and frictionless, then then the tensions T1 and T2 would be equal. If the pulley is not massless, then the tensions T1 and T2 would not be equal, and if even in if there is some friction in the pulley, so then in that case also T1 and T2 would not be equal. So that's an important point to note. So since it's an ideal pulley, then that's why the tensions T1 and T2 across the ends are equal. So then now we have the uh, free body diagrams of the components. So then we can just write down the differential equations. Now since K1 is positive towards the left hand side, we write down the spring force is negative. And similarly for the other mass, we can write it as m2x2 double dot. So these would be the equations of motion for this system. So since again we have two variables x1 and x2, that's why we have two degrees of freedom and therefore two equations of motion. So this is how we can solve this problem. So it's take 9 o'clock already. So we are coming towards the end of this session. So I was not able to cover the problems on pneumatic systems, but I will be uploading the solution when I share the slide. So I have the one more problem, example problem on pneumatic system. So I'll be solving and then sharing it on the slides. But we won't be able to discuss it in today's session. Apart from that, anyone has any questions, concerns, or comments? Sure. Yeah, thank you. Uh, so let us meet in the next week, in the next week's interaction sessions. So if you have any questions related to any of the course content or the content covered in this session, so you can always post your questions on the discussion forum page of the course, and so I'll try to answer your queries if you have any. And if you have any immediate questions, you can also ask them now. So I'll be sharing the slides and the recording of this session also. Sure. Sure. Thank you all for joining. So we can uh, end today's session over here.